Hello everybody, welcome back to our channel. In this episode we're going to be solving a Physics 7B fluid transport practice problem. As usual, if you're finding this content helpful, please make sure to leave a like and subscribe to our channel. It really helps a lot. So this is the problem that we're gonna be solving. Feel free to pause the video in order to copy the instructions or your notebook. So a pipe carries water from the bottom of a pool to the top of a water slide with the aid of a pump. The pool is 3 meters deep and the water slide is 5 meters above the surface of the pool. The pipe carrying the water has a uniform area. A diagram of the system is shown. So the first question is, if the pump's output is 62 kilojoules per meters cubed and the flow rate is 0.3 meters cubed per second, what is the resistance in the pipe? So as you can see, I have everything written down here. So we just need to figure out some distances by using the instructions. So the instructions say that the pool is 3 meters deep. So this distance is 3 meters. And it also says that the water slide is 5 meters above the surface of the pool. This means that this total distance, from the bottom of the pool to the top of the pool is equal to 8 meters, since this distance is equal to 5 meters, like this. So this is the 5 that the instructions are talking about. Then we have another 3. So now I know that from the bottom of the pool to the top of where the water slide is, we have 8 meters. Alright, so we need to figure out how to solve this problem. Now we have two different fluid systems. So we have a pool with water and the water is not moving. So this, the flow is equal to 0 over here. And we also have a little pipe that's connected over here and that goes all the way to the top. Now, by definition, these are two different fluid systems because they have two different flows. The flow over here is 0, and then we actually get a number. So the flow over here is 0.3. And what we have to figure out is what is the resistance on the pipe. So let's just go ahead and get started. So if I use my Bernoulli equation, first of all, I can't really use my Bernoulli equation from the top of the pool to the top of the water slide because, again, they are two different fluid systems. But what I can do is, because they are connected to each other, what I can do is start over here, go all the way here, and then start over here, and then sort of like go upwards like this. And if I do this, then at some point I'm going to be able to find the resistance. So let's just go ahead and do that. So I'm gonna start at the top of the pool and then bring this down to the bottom. So I'm gonna use my Bernoulli equation from top of the pool to bottom of the pool, like this, which obviously implies that I'm going, downwards from top to bottom, right? So this is delta P from top to bottom, like this. We have a change in height plus rho g delta y. We don't have a kinetic energy term because the water over here is not moving, and also the area is not changing, and it's just a pool. We don't have a pump when I'm going down like this, and we also don't have any flow because the water is not moving, so we don't even have to care about the resistance. So this is going to be equal to 0. Now, this pressure I'm gonna call PV, as in bottom of the pool, like this. But obviously over here at the top, just as this is open to the atmosphere, because you know it's just a water slide, this is a pool. So I mean it has to be open to the atmosphere because people swim on it, and like I mean pools are always open to the atmosphere. So if I go from top to bottom, this is P at the bottom minus atmospheric pressure. And this is equal to negative, this is water, so 1000 G is equal to 10. And this change in height is equal to 3 meters, except that I decided that I would go from the top to the bottom. So this is actually negative 3 meters, just because of the way in which I set up my equation. So this would be, so what is this? This is positive 30,000 pascals. So PV minus atmospheric pressure is 30,000. Now, what I'm gonna do is I'm gonna start over here at the bottom, and then I'm gonna go all the way up over here. So I'm gonna use my Bernoulli equation from the top of the pool to the water slide. So delta P plus rho G change in height. Now if I take this route, I'm actually encountering first of all a resistance, which is the thing that I have to find, but I also have a pump over here. So this is E pump divided by volume minus IR, like this. Now this delta P is final minus initial, so this would be P atmospheric minus P at the bottom, like this, final minus initial. And you can kind of see where I'm going with this. I'm gonna need this to help me out over here. Plus 1000, then this delta Y is this 8 meters over here, because I'm not going from this point to this point, I'm going from the lowest part of the pool all the way to the top, so this is 8 meters. And it is also positive because I'm going from the bottom to the top, so this is actually equal to positive 8. This is 62 kilojoules per meters cubed, so 62,000, and I is equal to 0.3 times the R that I want. Now I have two things that I don't know. So I don't know what this R is, and I also don't know what this PV is. But luckily enough, what I can do is, since I have this equation over here and I have this equation over here, and these two are kind of like opposites to each other, if I add this equation, if I add these two equations, I'm basically gonna be able to solve for R. So so if I add these equations, this would just be you know, these two cancel out, and this is just equal to 30,000, so negative 30,000 plus 1,000 times 10 times 8. And then I'm already solving for R at this point. Feel free to, you know, use several steps of algebra for this. And this is equal to R. Now, notice that even though I said that I would be adding them, I put a negative sign over here. That is because if I were to actually add them, I would put it on the right side of the equation, but I'm skipping one step by just putting it on the other side. So I know that this might be a little bit tricky for some of you. Definitely feel free to just do this step by step. But basically this is gonna give me the value of R. So let me just go ahead and grab my calculator. Let's see. So this is let's see, negative 30,000 plus 1000 plus 10 plus 8 minus 62,000, divide everything by negative 0.3. So I get 40,000. R is equal to 40,000, joules per seconds, meters to the 6. Final answer. There we go. So this is my final answer for part 1 of the problem. So let's just go ahead and read part 2. So part 2 says, the pool is partially drained for construction. How low can the water go in the pool before the water in the pipe stops flowing? Okay, so this is an interesting situation because what we're saying for part B is that, the water is just going to start lowering up. Now, as we know, the reason why this is working is because the reason why water is going up, you can just tell by looking at this. So some of the reason why the water is going up is that there is a pump, but the other reason is because you have some amount of water over here. And when you think about it, this volume of water is kind of like pushing down. And as it pushes down, it comes all the way up here, right? Well, as this water level starts going down, there is less water pushing down like this, and we will reach a height at which there is just not enough water over here to be able to keep pushing water down and then up, so our water will basically stop. So what's going to happen at this critical height is that I is going to be equal to 0. Because as the water level starts going down, you're gonna reach a height in which the flow just stops, and after that it's actually gonna start running backwards towards the pool. But there will be a certain critical height in which we're gonna have that change of just going like this to just going backwards, because you don't have the pressure due to this water anymore. So we have to figure that out. Now, for this part of the problem, what's going to be very useful is that we already have our 2 Bernoulli equations set up. So let's just go ahead and use them. So our first Bernoulli equation that we had was this, and the second Bernoulli equation that we had was this one over here. Okay, so what we are going to do is we're going to use these 2 equations that we already have, but we just need to be mindful that some things have changed. So starting with this equation over here, so this equation over here, I'm just going to copy it as it is. Delta P plus rho G delta Y is equal to E pump divided by volume, except that now I want to analyze the critical height. So now there won't be an IR term anymore. So this actually is going to go away. So this delta P is still this delta P, which is P atmospheric minus P at the bottom of the pool. This term over here is still exactly this term, because even though the water is changing over here in the pool, this equation is from the bottom of the pool. Why did I write? No, this is from the bottom of the pool. This is from the bottom of the pool and it goes to the water slide. So this equation starts here and ends here. So even though the water level is changing, this difference in height is still going to be 8 meters. So this term is going to look exactly the same. And the pump is still the same pump, so this is still 62,000. So now this delta P is just equal to 62,000 minus this number. So I'm just going to calculate that really fast. So this is 62,000 minus 1000 times 10 times 8. So this is negative 18,000. Now the other equation that I had at the beginning that I can modify is this equation over here. Now this equation over here was start at the top of the pool and end at the bottom of the pool. And it used to be the case that this delta y was 3 meters. But now we don't really know what the change in height is. That is actually what we're trying to figure out. So this equation was PB minus atmospheric pressure plus rho g change in height, and this was equal to 0. Now this number over here is just the opposite of what this number is, right? So I can just take this 18,000 and flip it and put it over here. But I do need to flip it because this is ATM minus bottom and this is bottom minus ATM. So this is positive 18,000 plus 1000 times 10 times delta y is equal to 0. So delta y is equal to 18,000 divided by 10,000. Then, oh yeah, negative of course, because we went from top to bottom, so yeah, so it makes sense. So the change in height is equal to 1.8 meters. So this change in height is equal to 1.8 meters. But now if you go back to the question, what the question was answering is how low can the water go? So the water started at 3 meters, and then at the lowest level is 1.8 meters. So basically the lowest it can go down is 1.2 meters. Final answer. Just because they weren't asking what is the new height of the pool, they were asking how low it can go. So if it can go down to 1.8 meters, then that means that it went down 1.2 meters because the original height was equal to 3. So that would be the final answer for that. And now for part C, we have after long use, the sediment builds up in the pipe, increasing the resistance. Okay, so for part C, the resistance goes down and decreasing the area of the pipe. Oh no, the resistance goes up. Sorry, what am I doing? The resistance goes up, but the area goes down. So basically this pipe gets clogged. So because now there's like rustiness on the pipe and like it's very rusty, and you know, so the resistance is now higher, but the area now is lower. And the question is, how does these changes affect the current in the pipe? Well, the area, first of all, is not going to change anything. Well, I don't want to say nothing, but area does not change the current. Changing the area is going to result in a change in velocity. So yes, if you decrease the area, you're going to have an increase in the velocity of the water. But there is a difference between velocity and flow. So you're not going to change the area. You're not going to change the flow, but decreasing this will increase this and the flow is going to stay the same. So the area is going to do nothing in this case. However, the resistance will. Because if you increase the resistance, then the resistance does directly affect the current because they are connected on the Bernoulli equation. So changing the area is not going to do anything to the current. It will increase the velocity, but it's not going to change the current. But increasing R basically means that the current is going to go down, meaning that as this thing gets clogged and rusty, it's going to be harder for water to flow through it. So the flow itself is going to decrease due to the resistance. So that would be our final answer. So I really hope that this video was useful. If you have any comments or you have any questions, please let us know in the comments on this video, and I will see you in the next video.